All right, this is my assignment 3. I'm going to go through it in Photoshop. I thought that would be super fun because I did that first quarter with the functions encyclopedia assignment. Made it all in Photoshop, so I'm kind of doing that again except with a video. So, assignment 3 by me. And I decided to do question 5. I thought it was a good one because I didn't need to use Desmos for it. And I think I demonstrated some core competencies while I did it. All right, so the restrictions on this one were jump discontinuity at x equals 3, infinite discontinuity at 1, and f of 2 equals negative 3. So one thing at a time, I started by finding a function with a jump discontinuity at 3. So I know that if you take x and apply a babysitter and a troublemaker to it, then you make a point discontinuity. And I figured out that if you put absolute value signs around the top, then that point discontinuity becomes a jump discontinuity because the graph gets like inverted between 0 and 3. So this function here created the jump discontinuity I wanted. So that was the first step I did. Next, I found a function with an infinite discontinuity at x equals 1. So I know that 1 over x has a vertical asymptote at 0. So I just needed to apply a horizontal translation, 1 to the right. So 1 over x minus 1 has a vertical asymptote where I want it. Now, I know from math, maybe 11 or 10, that when you add functions together, you can find like say f of 2 from the first function and the second function and add them together and add the y coordinates together, and this will give you the y coordinate for f of 2 from the function of those two functions just added together with a plus sign. Didn't explain that very well, but I think you know what I mean. So I figured that I could take this function here, my rational function, and simply add it to my jump discontinuity absolute value function. So it would look, I'd add that to that, and that would create the infinite discontinuity from that vertical asymptote at x equals 1. Because since that asymptote is infinite, adding it to another function will make almost no difference to the asymptote. So it'll still maintain its properties. So that's what I had so far. So now I needed to make sure that f of 2 equals negative 3. That's the last restraint on this function. So I started by taking f of 2 of what I had so far and solving. And when I did the steps, it gave me negative 1. Negative 1 does not equal negative 3. But it's close. I just need to move the whole function down 2. Right? So I just applied a vertical translation down 2. My final function came out to be this. Now, I could have simplified it, but I decided not to. It can be simplified a bit, but not that much. And it makes sense to me in this form because it has my 3 different functions that I kind of put together to meet all the criteria. Okay, next step, I stuck it in Desmos to graph it, see what it looked like. And this is the result. And it does indeed meet all the restrictions I intended it to. It has the vertical asymptote at x equals 1 right here. F of 2 equals negative 3, as we can see here. And it has the appropriate jump discontinuity caused by those absolute value symbols around the top of the first part of the function. There's also an oblique asymptote at x minus 2, or y equals x minus 2. I found this a bit interesting because when I started making this equation, I started with y equals x and then applied the babysitter thing and the absolute values, but y equals x was what I started with, and then at the end I had the minus 2 vertical translation to make f of 2 equal negative 3, and the oblique asymptote happens to be y equals x minus 2, those things combined. So, I don't know, it made sense to me that this would be how it is. but it doesn't really matter because it doesn't affect the restrictions that I'm trying to meet. Okay, time to check algebraically. First I checked if f of 2 equals negative 3. It does. Just plugged it in. Infinite discontinuity at x equals 1. For this I just found the limit as x approaches 1, and I ended up with something over 0 in the equation when I did this, so I know that that is true. There is a vertical asymptote there. Now, jump discontinuity at x equals 3. So to do this, I needed to break up the absolute value part of the function into two different options with restrictions on them, and then solve for the right and left hand limits. So I just made a little graph of what I have in the absolute value symbols. And when you graph it, it looks like a parabola with the middle part inverted. So the part that would make a normal parabola is the positive option instead of the absolute value symbols. So the restrictions on it are less than 0 and greater than 3. So it looks like this. This is the positive one, and the negative one is just between 0 and 3. It's the part that looks like an inverted parabola. So now I was able to use these two different functions to solve for the right and left hand limits as it approaches 3. So as it approaches from the left, we use the negative one, cancel out the babysitter and troublemaker pair there, and it gives us negative 4.5. And the graph agrees with this when you approach 3 from the left. Now when you approach it from the right, you use the positive option for the absolute value part, and simplify it, take out the babysitter and troublemaker, and it gives you 1.5. Graph agrees with this, and negative 4.5 does not equal 1.5, therefore the limits are not equal, and there is a jump discontinuity. Yay! Alright, so that's it. My function met all the things that I wanted it to meet, and I first proved this by looking at the graph in Desmos and making sure it worked. I drew it out here, and then I checked algebraically using limits so that to make sure that it worked that way as well. So yeah, hope you're having a good weekend. Thanks for watching. Sorry this video is so long. I hope it wasn't boring. Yeah, see you Monday.